So I'm going to start introducing what do we understand. Can I see?
Oh, is it not moving? In just a second. We'll get there. We got a lot going on back here. That should go.
There you go. So let me start with what we, to define to you what is a cosmic ray. And that's an easy question, but not at all. I mean, we call cosmic rays any type of particle that comes from the universe and reaches here on Earth. Of course, they are traveling around the universe, traveling around in our galaxy, and some of them reaches, right? Now we think that most of them, I mean, we are pretty sure about that, most of them may be hydrogen or protons. We have two names for the same thing, right? Because, the proton seems, it is the nuclei of this element that we call hydrogen. But also there are other element nuclei that arrive to Earth, like helium, boron, carbon, magnesium, iron, lead, any element that you may think of. What is interesting, so what is interesting is that most of them are hydrogen, like 80-something%, and a few of them, like 3 or 4%, 2% are helium. And just like tiny percent is the other elements. But also when we talk about cosmic rays, we talk about other particles like gamma rays, neutrinos, neutrons, and any other particle that can arrive from the universe. But since what are more common are these nuclei, when we refer in this talk to cosmic rays, I'm going to be talking about nuclei that have a charge, right? And they are the nuclei of the elements. So, okay. So before we start this, just rephrase your knowledge about what is an atom. Right? When I was a kid at school, people was telling me that matter, just matter that forms our bodies and everything, was formed by atoms. Right? Atom is a particle that is neutral. What that means is that the total charge is 0. And that is because in its center has a nuclei made of protons that has a positive charge. They are particles. And they have also neutrons that do not have a charge, electrical charge. And around these nuclei, there are electrons. That's in the normal way here with us, right? This is just, they are neutral. But when they are coming from the universe, they have lost, so they haven't attract these electrons. So they move around with positive charge, right? The charge of the particles. If you may remember, this is the periodic table of elements. Maybe when we were studying this part was not there. But as you remember, what makes an element to be an element is the number of protons in the nuclei. And when we have the same number of protons and we have different numbers of neutrons, we call that these two things are isotopes, right? So we have one proton, which makes hydrogen, but it could be 1 or 2 neutrons, and there would be 2 isotopes. If you walk around this periodic table, you will see that the number of protons will increase in this direction. So hydrogen has 2 protons, but helium has 2 protons. Lithium has 3, and beryllium has 4, and so on. So as we go down in this periodic table, we get heavier and heavier elements. This table is organized according to the number of protons that they have, but also according to some chemical properties that they have. For instance, around here we have the gases, around here we have some solids, and so on. So this is what we know about the elements here on the Earth, right? On Earth. But as you know, people used to say, humans are made of dust of stars, right? That means that the matter that we are made of came from somewhere else. It was not produced here on Earth. Kind of, we will see that. It's not really true. Okay, so cosmic rays were discovered in 1900 year. It was discovered in 1912, but before that, it was observed by other groups that these electroscopes, an electroscope is two metal, I forgot the name in English. Lamina in Spanish. Foil, thank you. Two metal foils are just with another metal here, you know, as is shown here, right? And when this is in vacuum, right, this is in a bottle. So when you put some electric charge here, so the charge goes to these foils, and because they have the same charge, they repel, right? So it depends on the distance that they, you know, get, is the amount of charge that they may have. So they use this to measure amount of charge in the past. But what they started to observe is that even though this was in vacuum, the electroscope was discharging. So the question was why and how. So people were thinking that maybe some particles were getting into the electroscope and discharged. That's how they found the natural radioactivity, right? That we have almost in everything. However, if that was true, it's not working anymore. Okay. So, if that was true, if what was discharged in this electroscope was the natural radioactivity, you should get the result that when you get further from the earth, I mean from sea level, or from, you know, the soil, you should get less and less and less radioactivity, right? And so this phenomenon should decrease. So Victor Hess and a few years earlier, Kurt Russell found Hess got into a balloon and measured the amount of this radioactivity, right, of this phenomenon at different altitudes. And what he found is that it was the opposite. He was expecting the number of particles or the number of these phenomena. He was counting pairs of ions at the function of the altitude decreasing. So he was expecting this line going down, but he found it going up. So it means that as far as you were going from land, you were getting more. So one of the explanations was then that this thing that was discharging the electroscope was not coming from the land. It was coming from outside of Earth. But still, that doesn't mean that it's coming from the universe, right? Which will mean very far away. It could come from the sun. So just to test that it was not coming from the sun, he made this experiment in an eclipse, right? When the moon was in front of the sun. So the moon should stop whatever was coming from the sun that was, making the electroscopes to discharge. But that was not the case. It still was. So then the hypothesis was that these things were coming from outside of the Earth, very far, even further from us. There were other persons making, experiments to find out more properties about these cosmic rays. In particular, what they did is try to measure the number of cosmic rays reaching at, the equator and at larger latitudes. And what they found is that as they were going to the poles, the number of cosmic rays were increasing, was increasing. What does that mean is that somehow the magnetic field of Earth was affecting the number of cosmic rays reaching us. Why is that? Because when we are getting close to the equator, the magnetic field is parallel to the land, so it doesn't let cosmic rays in. But when we are going to the poles, these cosmic rays, if they have charge, they are following the lines and getting through the poles. So then they thought, oh, maybe these cosmic rays have charge, right? Okay, so the question is, what charge do they have? Because it could have negative or positive. What kind of particle is that? And what they did now is to measure how many of these cosmic rays were coming from the east and how many were coming from the west. So if the charge was positive, that means that because of the magnetic field, the particles will be dispersed to the east if they were positive. But if they were negative, they will see the opposite. We will have more particles or just particles coming from east to west. This is a fun experiment because I was reading how they did it. And this was not a very sophisticated experiment. They went into buildings and they went to the east part and to the west side and do the experiment, right? And compare with the measurement inside. I just found out just a few weeks ago that Compton was in Mexico and that he was making one of these measurements. But I didn't see him, making any publication on that. But in one of the hotels that we are organizing a meeting of one of the experiments that I'm working on, which is not WIPO, it's HAWC. Compton was there. He was doing his experiment. And I was wondering, why did he choose there, which is in downtown? Well, because the buildings are made of, very wide walls made of rocks, right? So they would stop cosmic rays getting in. So they can be sure that cosmic rays won't go from west to side or to east to west. So since he didn't publish the paper, I think he was just a friend of, people working on that. In particular, Bruno Rossi, probably, and just being there, just having fun. Anyway, just after this story, say, this is just my guess, right? So then they found out that there were more particles, that they were. Now I spoiled my whole talk. Okay. So then what they found is that there were a lot more particles coming or traveling from west to east. So the conclusion was that these particles have to have positive charge, right? Which is in agreement to what I told, right? That they were hydrogen products with positive charge. Okay, so the study didn't finish there. There was this other guy, Rossi and Oyer. So Rossi noticed this result, but Oyer actually made a measurement of motion. And what they noticed, Rossi noticed, is that he had two detectors, two Geiger detectors, and once in a while both were triggering at the same time, simultaneously. And of course, maybe he didn't believe in gas. So he was wondering why that was happening. So probably he made a calculation on how, just by causality, this may happen, and he found that this was not normal. So his interpretation was that there may be something that connected these two things, right? These two detector measurements, right? That they were just triggering. So they started to think about something happening you know, at higher altitudes, triggering these two things connect. Auger, I mean, the development after that, the technique of coincidence was developed, right? I mean, it's not easy to conclude or to conclude that two things are happening simultaneously with enough time resolution. We somehow have to have two clocks synchronized, and that's not easy. Anyway, so the technique was developed so that we can measure at some given precision the coincidence of these two events. And also, they developed these kind of detectors. We are still using them. They are very easy to build, just, you know, for outreach. You have like a box. Yeah, it could be transparent. You make a block inside, like let's say with alcohol, you let the base cold, and since the bulb is warm, then you make a block. And when particles go through this block, right, they ionize the gas inside, you know, the alcohol, and they produce a drop, small drop. So, and they do all this through its path, I mean, their way through the box. And it's how you see that, for example, this particle is coming from here to here, right? You can see their path. They call these cloud chambers. So they made an array of these cloud chambers, right? And they took a picture of what we know is a particle air shower. So here, one particle arrived to this chamber. Somehow these are coils of very heavy elements so that they interact with this. And, you know, this is a particle reaction. They break the molecules. And then all the particles that are produced take a piece of the original energy of the primary. We call this the primary. And they travel, you know, down to this array of cloud chambers. And they, in their way, they do the same thing done as a primary, right? They interact with the molecules, break them, and produce more particles, give them some energy, and so on. So the particles down here have small pieces of the total energy of the primary, and we have a lot more particles here. So this is a particle air shower. What is amazing is that Auger made this, and the shower that he was measuring had, you know, between one of the detectors and the other detectors was at least 100 meters. So the shower had this extension. Today, today we know that there are cosmic rays that get into the atmosphere, produce these showers, and the extension of a shower could be kilometers, right? So imagine the difficulty of determining if all these detectors that we have on the surface are triggered in, you know, synchronized. So anyway, so this was the beginning. And then after that, they started to put magnetic fields and see that finally, depending on in which direction they were dispersed and how was the deflection of the trajectory, they could determine the mass of the particle. So that's how they found that most of them were protons and not, for instance, iron, right, or magnesium. So that they were light particles. But light, not as light as electron, but light in terms of the elements. So right now, you may say, okay, Magda, now we know that we have particles, mostly protons, coming from the universe, right? And so I would like to know, where are they produced and how? And answering that question is not only about cosmic rays, it's also knowing what is the origin of, you know, the elements that form matter here. So just just because of that, it's an interesting question already. But we will find out that these cosmic rays have different energy. Some of them are not too energetic, and others have like million times more energy than the ones that we call not energetic. But the ones that we already call the not energetic have the energy of particles that are a product of a nuclear one. So they are already very energetic. So the point is that we may know in the universe, or we may believe that we understand the universe enough to kind of point out to the guilty one, right? Who is producing these cosmic rays? But we will see that maybe not. I think it gets disconnected, yeah. So the question is how they are produced, these elements. And now I have the same periodic table, right? But they are organized in the same way. But now the different color code. And here I want you to see that the color code means where are these elements produced, or where we believe they are produced. So you see that the lightest ones, like hydrogen and helium, are produced in the Big Bang, at the beginning of the universe. Then we have some of them that are a little bit heavier, that are produced as what we call cosmos. I'm going to explain this in a moment. But most of them, the greens and the yellow ones, are produced in spins, and also this kind of red, are produced in stars of different mass. The stars as our sun, or stars that will produce big explosions that we call supernovas. But this happened only in the last years that we had another color, the violet, purple, or whatever you call it, which is the man-made elements. These elements are only here on Earth because we have produced them, right? So we are contributing to this. So, how is this happening? Let's start at the beginning. We have the Big Bang, right? This moment where everything was in a very tiny space. We didn't have humans, we didn't have stars, we didn't have atoms. We have only the fundamental particles and air all together. So we have this explosion, all this was expanding, creating the universe. And after it cooled down enough, then we have some particles, some fundamental particles that we call quarks and electrons. We've got the quarks getting together, right? Because at the beginning, all the forces that we know, the gravity, electromagnetic, weak force, and strong force, were forming a unique force. But when time was going on, then they were separated, and then the quarks got together in the strong force. So then they started to form protons and neutrons, and as they were cooling down, they were able to get together protons to produce helium, right? But you see that it happened 10 with 13 zeros seconds. And then after another 1,000 million years, we started to have elements. And when I call elements, I mean that they started to attract electrons, right, to get neutron. But it was only in the last part of this evolution of the universe when we have the heavy elements. And this is because, as I said, we need stars, right? And we need massive stars. Okay, this is just a summary of what I said. I'm going here. And what is this? And how this happened? This is how we think it happened. As you may remember, we have a star, we have gas, hydrogen, right, that by gravity gets together, right? So gravity brings it closer and closer and closer. So it starts to make some pressure on this material, So they get together and we start to have a fusion, right? So we overcome the electromagnetic force that will push them away because they have the same charge. And finally, we get them together. So in that process, we release energy. But the heaviest element that we can make in this way is iron, only iron. So we have the star, the gravity is pushing together, so it warms up. This energy makes the elements, the nuclei get together, burn, and produce two hydrogens, helium, and from helium, carbon, and so on and so on. Until we get iron, and then the stars cannot form material and gets to the end of its life. If the star is very, very massive, then it will explode and produce a supernova. But in this process, we cannot produce anything heavier than iron. Okay, but if the star is very heavy, we have other processes that may happen that we call process R and S. R because it's rapid, and S because it's slow. You know, I always say that scientists are very intelligent when we name things. Right? Like in cases of gamma rays, you know, the gamma rays that we know hit on Earth are called just gamma rays. But we knew later that gamma rays could have more energy. So we call them high energy gamma rays. But then we found out that there are even gamma rays with even more energy. So we call them very high energy gamma rays. So anyway, I don't say that, criticize my colleagues. So what happens in these processes? Well, it happens that we get an element that captures a neutron, and this neutron, by the beta process, which means that it will convert to a proton and liberate an electron, can convert to another element. So this happens very fast in supernova and slow in not such as massive stars. Just to give you an example, there is something that we call kilonova. And people was predicting the kilonova, which is not as energetic as the supernova. But we thought that elements, the heavier elements, were produced there. And that was proven in 2017 with a gamma ray burst that had associated a gravitational wave that was even observed. So this is something that has been proven just in the last years. Okay, so we have the supernova where we have just a set of elements that we can produce. As you can see, we produce a helium, carbon, oxygen, and so on. But for example, lithium is not here, or boron is not here, right? So we cannot produce all the elements, even if they are not heavy with the supernova. Or it's what we thought. But what we know is that when these particles go and travel through the universe, they interact, they have reactions with matter, you know, that they encounter, and they will interstellar medium, and then they produce the other elements. So we call these primary elements, and we call these secondary elements. Again, you know, next. So so the question now is, okay, so now we need to know what causes these very big explosions, right? And check that everything is in order, that we understand. Right? So we study those phenomena. I think I need to click here. One of them is what we call gamma ray burst. We know that they produce supernovas, kilonovas, and all that. We know that there are short gamma ray bursts that last only a few seconds, and they release a huge amount of energy, like all the sun just converted to energy and release it less than 2 seconds. So as you see, you will have two compact objects. This means a star that is very small, for example, a neutron star or a black hole. And they lose their energy, gravitational energy, so until they collapse and produce a big explosion. We could have that a black hole or a neutron star is or creates another companion star, right? So it gets very close until it breaks it and attract all this matter until it explodes. Or we could have a very massive star that cannot burn any more material because it's very massive and it doesn't have any more, and then explodes, right? This will produce also a gamma ray burst, but the duration goes is larger than 2 seconds, and it can last like 1,000 seconds. So we are studying them. Actually, right now we have observed like more than 10,000. And I used to say that when we observe one GRB, we are observing just one GRB because it's completely different to the others, right? So even though we have thousands of them, we still do not understand them. And even we believe that they may produce cosmic rays, we haven't proven, we haven't observed a totally evidence that that is happening. We also study AGNs. AGNs are a very massive black hole that is accreting mass from the galaxy that is encased in the center of our galaxy, and is radiating energy through two jets, one in the opposite directions. We are also studying them, and people really think that they are the accelerator of cosmic rays, but still we are not completely sure. So, yeah, the question is like, Magda, why do I care? And I always get this question. I mean, how does that affect me, Magda? Why should we pay for you to do that research, right? Who cares? I mean, and the usual question is like, it's the universe, you want to know about the universe. And sometimes we get, okay, fine, I want to get an answer about the universe. I may want to get an answer about why I am made of these kind of elements and where they're coming from. That's enough to give you millions of dollars, right? So the first thing that I can tell you is like, oh, you see, they also produce nice things, right? They produce the northern and the southern lights. They are made by these particles, right, that are guided by the magnetic lines of the magnetic field of the Earth, and they get into the hole. So when they are too many, they ionize the molecules in the atmosphere, and then they radiate as beautiful light with different colors. But guess what? There are some scientists that believe that cosmic rays also are the seeds of clouds. Right? So if we have too many cosmic rays, we may have more clouds that we were having. And if we have too many clouds, then the temperature will go down. There is this experiment. People is expending money trying to prove this. So in CERN, they have this experiment called cloud. They produce a type of atmosphere inside of this container, which is very big. And since they have a lot of particles because they have the accelerator there, they are trying to prove that they can produce clouds. And that they can, actually what they have found is that the number of cosmic rays getting into this container determines how many aerosols are produced. And that determines also the number of clouds that we do when produce. So here, there is some measurements. You know, this is time years, you know, this is the year 1984 and so on, and this is 2000. And this is the percentage of clouds that we may have. And these are the number of cosmic rays that we measure that were arriving at that time. And you see they are, I mean, this is obviously, this goes from lower to higher, but this goes opposite, right? So they are correlated, right? As we have more cosmic rays, we have more clouds, except in the last year. But that's because of a different reason, right? That's because now we are modifying our atmosphere, right? With burning fossils. But also, because of this, people believe that could be some of the consequences of extinctions, right? For different reasons. They say, what happens if we have a supernova explosion very close by? You know, supernovas could be a different distance. And depending on the distance, could be different consequences to us. So they can think that, for instance, it could cause mutations, right, to animals and vegetables that we may have here on Earth. And these mutations could be good and bad. I mean, mutations are not bad at all. We mutate, I mean, we are getting cosmic rays all the time. And they cause mutations in, you know, the cells that are being reproduced all the time. And our body is capable of just getting that and say, okay, you are not passing the quality, just go away, right? And just move it. And sometimes they produce a different individual. And that individual could be better or not, in the sense that it could survive better or not. And that's why how we improve or not. Right? So, but what's happening? We have too many mutations, and if they are not good enough, so then we can get extinct. But they also talk about, you know, for instance, if we have too many cosmic rays, we may have an extra radiation by X-rays. Or if we have more or less clouds, we may have more or less ultraviolet clouds. And that could damage the life, right? And as I said, could also change the number of clouds, you know, on Earth, and that could get the temperature lower until, you know, life will not survive. So they are taking, you know, measurements, they are making studies and trying to see if this was one of the reasons or not. Like 5 years ago, 2 years ago, I found one study where they were having temperature and you know, different extinctions. And somehow they were able to make an estimation of cosmic rays. And they were, and I'm not saying how this was happening. And they were saying that they may be correlated. But I haven't found it. So I don't know if they just took it away because they couldn't just, you know, support it or what. I don't know. But you see, this is a study that was just published in 2020. So I'm saying that this is, you know, something being investigated. But guess what? These cosmic rays, because of their energies, they interact with things of the size of nanometers, right? And right now, we are so happy of having electronics of the size of nanometers, right? So they interact with this electronic, and they are causing problems, right? Because they release energy in a very short time to these electronics. So now, there are some airplane accidents that have been associated to this kind of effect of cosmic rays modifying or changing the lectures of the electronics of airplanes. But you see, this is in Japan. This is here. I think this is. I forgot if this is No, this is France, right? This is everywhere. So now people who is working on electronics, they have to take this into account, especially if you are going to take these instruments to the space, right? In spaceships. So yeah, we should care about it. If you are worried about your radio, your car, don't worry about that. Don't. That's not a problem. But also, cosmic rays generate carbon-14, which help us to get the dates of many things, many materials, right? How we get the age of materials. And cosmic rays are supposed to maintain the same level of carbon, in the atmosphere. The problem is that we humans are modifying this. So cosmic rays now cannot keep the same levels of carbon-14. So now people get harder and harder to use it to get the age of things with carbon-14, which is not a big problem, maybe, right? But also, maybe you also learned this at school when they were explaining, oh, what's the nature? I mean, how is a lightning produced, right? And they say, oh, the clouds, the sharing between clouds separates, the positive charges or the negative charges, and when that's enough, boom, the lightning is produced, right? So this charge is produced. Well, that's not enough. That's not the whole stuff. When it's something that triggers this process, and people think that our cosmic rays were perceived also as lightning. And to tell you the truth, we have this experiment in Volcano in Puebla, as I already told you about that, which is called HAWC. And we have observed that when we have storms with lightning, the number of cosmic rays or the particles that we measure with our instrument increases. So may be related. We have some of our colleagues studying this. And we have now instruments to measure the distance of the lightning and to try to get some information. But also, they contribute to the radiation that we normally get, right? It is about 13% of the radiation that we get at sea level. So if we go to a volcano, or if we get into a balloon, or if we go to a spaceship, we will get more radiation, and that's important to understand for astronauts. Okay, so now I may convince you that we do it, right? I mean, that is not that I want money to do research about something that's passionate, right? It's something that we should care about, that changes our normal life more now that we have cell phones. But then you may be asking, okay, Magda, but what changed the number of cosmic rays that enters Earth? Okay, so one is the activity of our sun. When the activity of our sun increases, the number of cosmic rays that reaches us are less. Why? Because when the activity of the sun increases, it gets on a lot of particles, a lot of mass, solar mass, to the space, and that works like a shelter. No, yeah, it's good. Yeah. So that's why we get less, right? And that's how we measure. We know pretty much about that. These are, that the sun has cycles, right? Every 11 years, changes the activity, it increases and increases, and so on. And this is just these are the cosmic rays that we are getting, and then you see when it's less activity of the sun, is maximum the number of cosmic rays that we get, and so on. And these are very different measurements from different instruments. And I'm just putting this here, not because I want you to understand, because this is enough, but just to say, you see how is there. So this is another sort of the experiment that I'm working on. So that we can see the change of cosmic rays when the activity of the sun changes. But also, you see, we travel around the galaxy. And sometimes we go through the spiral arms of the galaxy. And what happens in these spiral arms? The density is more. And if the density is more stars, massive stars are produced and supernovas can be produced. So that means that cosmic rays arriving through the Earth to Earth increases. So this is the trajectory of our solar system through the galaxy. As you can see, sometimes we go through these spiral arms, which are the gray path, and sometimes we don't. So remember that I told you that some people is trying to correlate the cosmic rays with extinctions. So they believe that when we were going through these arms, since the cosmic rays increases, then we have more clouds, then the temperature went down, and that causes the extinction of dinosaurs and several extinctions. And they were associating the timing here. But as I said, I didn't find that result in the last year, so I don't know what happened with them. Okay, so now we know what modifies how many of these cosmic rays we get. But now I want Magda to tell me where they are originated. But before that, let me tell you what happened with these cosmic rays from the place where they get originated to their travel to the Earth. When they travel around the universe. Since in the universe, when they get into galaxies and all around the universe, we have magnetic fields, and they have charge, so they get deflected, right? So by the time that they get to the Earth, if it was produced there, it will come from there, because it does all the information about it, where it was produced, because it was reflected in its way to the Earth. The less energetic will be more reflected, and the more energetic may keep some information of where they are produced, because more or less they are deflected for a few degrees depending on how far is the source. So that's why there is this experiment in Argentina called the Observatory. They have different detectors in a kilometer square area, and they are trying to measure where these cosmic rays with the highest energies are coming from. And they are trying to associate them to populations of AGS, Arctic galactic nuclei, or gamma ray bursts, or supernova remnants, or anything, just trying to find out where they are coming from. Or if there is just close source that may produce it, but we have. But the these cosmic rays that are produced within the galaxy, right? When they get, before that, when these cosmic rays get into our galaxy, they find a lot of matter. They find molecular clocks, right? And what they do is they have particle reactions. What that means that we have one proton or one nuclei that interacts with material of these clouds, and they produce another particle that is called ion, and then they produce this ion decays and produce electrons, neutrinos, and gammas. But what is important here is that you see there are no more protons here. So the proton disappears, but we have gammas. The gammas is light. The gamma rays are light with the highest energy. So what it means is that in any place where this cosmic ray interacts with matter, there will be a glow, right, of gamma rays. So now we have measured the galaxy glowing, right? You see all this red is gamma rays being produced, most of them, produced by the cosmic rays interacting with the matter there. And I think I put it there. So if I could have a map here of how the matter in our galaxy is distributed, we have this shape. So we appreciate that it's happening because so some of them interact, but some with more energy will get to Earth. And some may produce in the galaxy. So the ones that arrive to Earth, as I said, some of them are blocked by our magnetic field, but some of them will follow the magnetic field lines and arrive to the poles and produce titan. If they have more energy, some will be absorbed by our atmosphere, which is the role of our atmosphere. So that's why we should take care of our atmosphere. Because if it doesn't do this, then these cosmic rays will reach us, right? And that will be radiation, more radiation in our bodies. And then, but some of them, the most energetic, will get air showers because of the atmosphere. And then I will show you how this happened, you see? And these particles would get to the surface. So we thought we understood. We know this is energy, this is a number of particles. You can see, as I told you, you see this is the energy that is equivalent to the nuclear bonds. And this is just, let's say that this is unity. Between this and this cosmic rays, there are 12 zeros, right? Like a million more energy. But if we have this amount of cosmic rays at this energy, you can see that we have 0.00000 less cosmic rays of this energy. This means that the cosmic rays with the highest energies that we know comes one of them per century per cubic squares. So it's very hard to detect one. So we have not detected too many. Well, these cosmic rays are accelerated because of the connection of magnetic fields. We have seen that in the sun, but it's not enough to produce the most energetic ones. We know that they are produced in what we call a shockwave. Shockwave, just to understand, is that wave that is produced when the source moves faster than the velocity that we can communicate that something happened there. For example, is what produces this phenomena when airplanes fly faster than the sound, the velocity of the sound, or a dog moves faster than the waves can move, or what we produce in nuclear bombs. But also they are produced, they are the reason why we have these arms. This is a discontinuity of density, and also when we have a big explosion as a supernova. So that's why we believe here could be the places where we produce cosmic rays, of course, not in the waves of the dog. And how this happens, you know, when you are, swimming in the sea and boat passes with very high speed. When you go through this part, this wave, you feel that you are getting energy, right? You feel it. It's how the particles get this energy. Okay. So the point is where that happens. So in order to give them energy, we need to confine them. And the way to confine them is with the magnetic field. We have done it. We learned about it. That's why we have this accelerator at CERN. So when we see the magnetic field of some astronomical events versus their size, we can see what are the possible sources of cosmic rays. So some are, the active nuclei in some galaxies, some in gamma ray bursts, and those are the sources that we are studying. So we know that some cosmic rays may interact with matter and produce gamma rays in neutrinos. So other way to study cosmic rays is measuring neutrinos and gamma rays. And that's how we do it. We have several instruments in all, around the world, measuring different particles, right? Like Hawk, the experiments where I work on, like Whipple. You see here, I don't know, I think very, yeah, it's something, right? Whipple, okay. They measure gamma rays. we have Euler, which measures cosmic rays. And I should have here Antares, right? And ice cube here, which measure neutrinos. And that's how we study, and this is the way that we are trying to understand the origin of cosmic rays. And that will bring me to show you how it looks like. And this is a better picture. This is in the volcano Sierra Negra in Mexico. Mexico is around here. Puebla is there. If you haven't been there, we are close to the top of the volcano. And this is how it looks like. And I would love to tell you the beautiful results that we have, but that's probably better. Thank you.